So one more thing about, because I might forget to bring this up at a later point, that another idea about the basis function is that if you have some point, that point is described by an x and a y coordinate. This x and y, as we talked about, you can write a function that tells you, oh, well, okay, so you got a point at x. So you write a function that gives you a point of 1 along x and 0 everywhere else, so that when you take a number or any other function, you multiply it, that will always give you this x point. And likewise for the y, we're just taking this basis function, we're rotating it by 90 degrees, and we're creating a function here, eigenfunctions, basis functions. Kind of the same thing, kind of. So basically what we're doing then is we are basically taking a function of radius 1 and we're rotating that by 90 degrees to get our two basis functions for here, for our x and y point. This is y, and we could keep going around the circle. This is why in computer science we're able to take basically a two-dimensional array of points like this and turn this into a one-dimensional array, because what we do is we just take this section, we put it up into here, so we rotate this basis function, we rotate this basis function, and you get a list of points. And how do you offset that? Basically by the amount of times you go around this loop. And that's what we call modulus. The absolute value, related-ish. And then also you have the angle, which is the imaginary component, et cetera, et cetera, et cetera. And generally this is what you would call the imaginary direction, because your imaginary number is z to the I, ix plus, I can't remember off the top of my head, but my point is that that this is a vector. The I is going in the imaginary direction or y direction. It doesn't matter if it's whatever you want your plot to be, right? So, so this is equal to your complex number. So complex numbers are related to how many times you go around a circle. It's related to how many times are you needed to basically explain a wave. If you can explain the wave in one shot, then you just need sine and cosine. No big deal. If there's a lot of noise, you need more things, and you need your Fourier analysis and your frequency. And because, again, just to prove this, if we need this from this point to this point, if I'm only talking about a signal that is just a sine wave, I can explain everything with the wavelength, or the wavelength is proportional to the period, right? So if I know how long between these points, I can relate that to my frequency. And I may have screwed this up. It's equal to HF, which is equal to HC over lambda. See if I ever remember which, if I ever forget which, I just bust out this formula and see, again, basis, sparsely sampled points. This is one of my bases that I use in learning, because I can always use this to help me figure out and remember what the relationship between lambda and everything else is, because it is a basis of this equation, F, H. So F is proportional because we could just cancel out the H, and then we get not really C, it's velocity, but it's supposed to be C. And there, so you have that, so this, and then after this, you know that 1 over T is frequency. Basis functions. They tell you what direction you're going in so that you can work out and make predictions. So pointers, literally.